topic that I chose to talk about was angular momentum. Angular momentum incorporates many different aspects from physics and biomechanics to understand how objects and bodies move. One must understand velocity, moment of inertia, as well as the different laws of motion in order to fully understand angular momentum. First off, moment of inertia describes an object's resistance to angular acceleration. A larger moment of inertia means that more force is required to observe a change in angular acceleration when compared to an object with a smaller moment of inertia. This is due to how the equation is set up. We know that the moment of inertia equation is moment of inertia equals mass times radius squared. Therefore, if a baseball bat has more mass located closer to the handle, it will require less force to swing when compared to a bat that has more mass located at the end of the bat, since the radius will be smaller. The equation for angular momentum is moment of inertia times angular velocity. We know that moment of inertia can be rewritten as mass times radius squared, so angular momentum can be rewritten as mass times radius squared times angular velocity. It is also worth noting that angular velocity can be rewritten as linear velocity divided by radius. Therefore, angular momentum can be rewritten as mass times radius times linear velocity. Angular momentum is also a vector quantity, meaning it has a direction and numerical value. For the direction, one must use the right hand rule with 4 fingers pointing in the direction of the motion with the thumb extended. With the thumb extended in this position, it will tell you the direction of the angular momentum. With all of this being said, let's look at an example of angular momentum in action to help us get a better grasp on the topic. Let's look at this basketball for example. If I spin the basketball at a fixed point, the distance from the fixed point to the edge of the sphere will be the radius. As it is spinning, we will be able to find a linear velocity at any given point in time. With these variables, we will be able to calculate angular momentum by taking the mass of the basketball times the radius times the linear velocity that we found. Granted, for this example, the conservation of angular momentum will not apply since friction force is causing the angular velocity of the ball to decrease until it eventually reaches 0. I will talk about this more later. Angular momentum is still similar to linear momentum in the fact that it follows Newton's 3 laws of motion. The first law describes that if there are no external forces or torques applied to the system, then the momentum will be conserved. The second law describes how if a torque is applied to the object, then there will be a change in angular acceleration on the object, just as if a force is applied to an object, then there will be a change in the linear acceleration of the object. The third law describes that for every torque exerted on the object, there's an equal and opposite torque exerted back. The final thing worth describing for angular momentum is how angular impulse is related to it. Angular impulse will equal the change in angular momentum of the object. This is described by combining a few equations. First, angular impulse equals sum of torques on an object times the time that these torques are applied to the object. Since we know this equals the change in angular momentum and moment of inertia will remain constant, we can rewrite this as sum of torques times time in which torque is applied equals moment of inertia times change in angular velocity. With all this information, one should have a good idea on how angular momentum applies to objects that are equally distributed in mass and have a fixed point of rotation.